project, the goals we aimed for were a thorough understanding of the fundamentals of soil mechanics, the ability to solve complex problems as part of a group and as individuals, the ability to design, carry out and report on the experiments, the ability to discuss your understanding with peers and tutors, and the ability to work as part of a group. The aims of the brief were as follows: to create a water detention pond to provide the university with grey water, to create a berm with a maximum height of 5 metres, to investigate the different types of soil below ground level through lab and field tests, and to produce a final design and method of construction of the berm. Shown is an aerial photograph of where the detention pond is to be built. We carried out a site investigation to investigate the different stratums within the soil, and we carried out both lab tests, which I will discuss later, and field tests. These tests were then gathered to help produce a final design for the berm. One test we carried out on site was the shear vein test. The shear vein test is a cheap and quick way to measure the shear strength of the soil on site. The apparatus is inserted into the soil and the top is rotated slowly clockwise until you feel the soil shearing, and once extracted it gives a reading in kPa. At 1.5 metres the max shear stress was 46 kPa, and at 1.65 metres the max stress was 79 kPa. This is quite low, most probably because of the silt soil. Each group dug a trial pit. Our pit consisted of 650 ml of topsoil, 300 ml of peat, 700 ml of silt, 200 ml of wet sand, another 650 ml of silt, and 800 ml of clay. Here's a list of safety options we observed when digging the trial pit. Each student had to wear safety boots, a high visibility vest, and a hard hat on site. Care had to be taken into account while looking down into the trench and to avoid obstructing the pathway of the digger. No person may enter a trench which has a depth of 1.5 metres or more. Now we come to our soil testing. We did 6 soil tests overall. We did plastic consistency testing, which is the liquid limit and the plastic limit tests, the Proctor test, the MCV test, the specific gravity test, and the permeability test. The liquid limit test was done using the pentrometer to penetrate the soil at different moisture contents and record the results. Shown are graphs of penetration versus moisture content of clay and silt respectively. At 20 ml penetration, the liquid limit of clay was 56.5% and of silt was 29.35%. Since the liquid limit of silt was so poor, we decided to scrap further tests on silt to save time for other tests. The plastic limit test was done using the worm rolling method. We rolled the clay into 3 ml diameters and then added water until it stuck without cracking. After we found the plastic limit, we placed it in the oven to find the moisture content. The plastic limit was 28.42%. From this we could get the plastic index. This is done by taking the liquid limit from the plastic limit, whose result was 28.42. Because this is a relatively low plastic index, it means it is less susceptible to swelling clay conditions. The Proctor test is used to determine the maximum dry density at the optimum moisture content. The procedure is as follows: weigh the 100 by 100 ml Proctor mould without the collar. Fill with soil 1/3 of the way up and hit 27 blows with the Proctor hammer. Repeat 3 times and scrape off excess soil once the collar is removed. Weigh the mould again to get the weight of the soil. Place the sample in the oven to get the moisture content. Repeat the process with different moisture contents. This video shows the Proctor hammer being properly used. As indicated before, there are 27 blows used per layer. This is the Proctor test results curve. It plots the maximum dry density versus the moisture content. The peak of the curve shows the maximum dry density for the optimum moisture content. As can be seen from our curve, the optimum moisture content is 21.4% and the maximum dry density is 2.122 kg per meter cubed. Similar to the Proctor test, the MCV test is used to determine the maximum dry density at a certain moisture content. The procedure is as follows: weigh the empty MCV cylinder, place about 1.5 kg of wet soil in the MCV mould, release the MCV hammer on the mould and record the level of penetration on the dial of the machine. Continue dropping the hammer on the soil up to 128 times and record at predetermined intervals. Remove the cylinder and weigh it with soil inside. Take a sample and place it in the oven for 24 hours to get the moisture content. This curve shows the graph of the MCV results. It is of n, the number of blows, versus delta P, the penetration. The maximum dry density of the soil at 21% moisture content is 2.125 kilograms per meter cubed. This coincides with our Proctor result, which ironically has a maximum dry density of 2.112 at the optimum moisture content, which is 21.4%. The specific gravity test is used to determine the density of soil particles, which was beneficial when constructing the berm. Shown is a list of weights of various components in the cylinders. By using the formula shown, we found that our specific gravity was 2.59. The permeability test is used to find out the rate water will seep through the clay particles and determine whether a membrane is needed. The apparatus was set up as shown in the picture. Once achieved, water was added and the straight height of the water was recorded. We came back after 24 hours and recorded the result. The coefficient of permeability K was 1.4 by 10 to the power minus 6. From this result we know that our berm does not need a membrane. This leads us to the actual design of our berm. Our objectives when designing the berm were to create a suitable berm for the detention pond which satisfies the brief, and to try and use the test result data and research to indicate which type of berm is best suited and decide whether a membrane is needed. These are the possible dimensions of our berm. It is 5 meters high with an additional 3 meters of excavation required on the water side. The average slope of a clay berm is 2:1. The side of the pond angle is 28 degrees. The angle of friction of clay is 30 degrees, so the berm has to have a smaller angle to stop it falling in on itself. The first option we looked at was a 100% clay structure. The advantages of this structure is that it has a high compactable strong design. However, some materials may need to be imported from other sites. Another option is to use compacted clay banked with silt at either end. A good advantage of this type is most of the soil extracted can be used to construct the berm. The disadvantages we found from testing and research is that silt is more permeable than clay, so it is under more pressure from shear stress from the water. This picture shows where shear stress will occur on the berm as indicated by the red lines. It can be clearly seen that the base of the berm is under a lot more pressure from the water. After considering the shear stress, the chosen design for the berm is clay because it has a stronger design overall. The silt edges would be more susceptible to this shear stress of the water. It is also less permeable than silt, which means it is better able to deal with seepage problems. We decided to place a membrane on top of 600 ml of sand as indicated by the diagram because organic soils are prone to sinking. There is no membrane required in the sides of the berm because the clay is impermeable. We also decided to place a step gravel filter at the base of the berm above the membrane to prevent seepage through the side of the berm. The more common seepage areas are represented by the red lines in the diagram. Our berm will be compacted in layers of 225 mm to comply with the regulations. Soil should be tested at regular intervals to ensure sufficient compaction. Plants such as rollers are used to compact the soil. Below is a list of health and safety precautions. Steel toe cap boots and high-vis jackets should be worn on site. Lab coats must be worn when carrying out testing. First aid facilities are necessary on site. A 2-meter fence should be posted around the lake to stop pedestrians falling in. Life buoys should be posted around the lake. Water monitoring should be carried out to identify pollutants. When we look back at our earlier goals, we feel that we accomplished most, if not all of them, through the various PBL sessions, research, lab time, and through interacting with our own group members, as well as various other group members. At the start of the brief we felt a lot of frustration at the lack of information in the brief, as well as how little we were being told about what was required. The PBL sessions were particularly difficult with such little information. We also had trouble converting the lab data into usable results for the berm design. Finally, we felt that by interacting with various people and consulting websites and literature, that we succeeded in creating a detention pond to an adequate level.